Hey everyone, thank you so much for watching another Weaviate release podcast. I'm super excited about Weaviate 1.18. The big theme of this is being speed, memory saving, some UX improvements like adding filters to hybrid search. So I'm super excited to welcome Weaviate CTO and co-founder Eddie Dillacher to explain some of the new updates to Weaviate 1.18.
Hey, Connor, thanks for having me.
Awesome. So we have such an exciting list from bitmap indexing and update to HNSW with adding product quantization and then the WAND algorithm for BM25 and hybrid search. So could we kick things off by diving into bitmap indexing and what's new about that?
Yeah, sure. Bitmap indexing is one of those things that the first time we saw it was almost too good to be true. I think at some point I tweeted out where we had like 1,000 times a speed improvement on a filtered query, and that was not just some marketing stuff. That was really we had a filter in a specific combination on 100 million data set where a filter could take I think something like 5 seconds. And now that same filter would take 5 milliseconds. So it's really a 1,000 times improvement. And the idea is basically we use for filtering, we use the inverted index, and the inverted index is basically the ground truth of what is allowed or disallowed. And then we pass that, we call internally, we call it an allow list. We pass that allow list to the HNSW index and say, like, hey, these are the X number of objects that you are allowed to use in your search, basically. And the problem there was if a filter suddenly matches the entire database on 100 million objects, then you would have, or you would spend so much time building up that filter from the inverted index that all of a sudden, like even if the vector search for a filter that matches the entire database, the vector search doesn't really care, right? It's like it's almost the same as an unfiltered one, or it is the same as an unfiltered one if it matches literally everything in the database. But that mere fact of building up the filter, that took so much time. And then we thought, like, okay, what's going on? What is happening with our current implementation, and what could we improve? And we came across roaring bitmaps, which is basically a perfect sort of fit because bitmaps or bit sets in general are made exactly for this. Like, is something contained? Yes, no. And it works with basically with increasing IDs, which is exactly what we have because of the inverted index already. So perfect fit. Only problem there was that sort of if you store your inverted index in a specific way and then you convert it into a roaring bitmap, which is what some other databases do, then you still have that cost of storing it in a different way. Basically, you still have that retrieval cost. And we said, hey, there's this one thing, and that's another tweet that I put out where at some point I said, like, we made that crazy decision to basically build everything from scratch in Weaviate, and that is one of the points where it really pays off right now, because we just put those roaring bitmaps straight into the storage layer, like in our LSM store itself. And that means we don't have to do any kind of retrieve then turn into a bitmap. So for example, you could do it that way if you had, say, a classical storage engine that would just store the roaring bitmap. Then you could still sort of retrieve the roaring bitmap, and you could do fast intersections like for an AND or operations. Once you have the bitmap, that would still be fast, but you'd always have that cost up front. But because we could build it straight into the LSM store, that cost is completely gone, and that gives us latencies in the single digit milliseconds for that filter part. So I think on the 100 million was our evaluation case, because there before we ran into those 5 second latencies, and then on that same case now a simple filter that matches everything is something like a millisecond or maybe two. And then even if you have some complex operations like range queries or merging different filters, this and that or that, like with multiple operands, that's all super fast right now, which is incredibly cool. One more thing to say about this. Of course, this is a very different way of storing and handling data in VBA in 1.18 than it was in 1.17. So listeners might now think, wow, well, what do I have to do? Like, is that going to break my entire VB8 instance? And the good news is no, it's not. So if you don't do anything, if you just upgrade to 1.18, it will just fall back to what it's already used to. But then you also won't have the speed benefits. But we also have a migration option, which you can basically run one time. You just start a VB8 with an option, say like, hey, migrate my indexes to roaring bitmap indexes, and then it will run through your objects once, basically with the first time it starts up. And VV8 will be in read-only mode during that phase, because of course when it rebuilds the entire index, then you can't have writes coming in, but you can still use it normally. It's only read-only, and once that is complete, read-only mode is gone, and you have the benefits of super fast filters in VV8 1.18 with your data that you imported in 1.17.
Yeah, that's extremely interesting, and yeah, that detail is super cool that you can just kind of update it, and yeah. So maybe kind of coming back into the application and motivating a little further. I remember like reading your article about pre-filtered vector search and 50 milliseconds and this kind of thing, and I always thought initially this idea of adding symbolic filters to the vector search was such an interesting idea. Learning more about how you use this allow list structure with the HNSW, like how technically that's implemented. So maybe kind of talking a bit about the applications and the tests a little more. I really like these things. Like when we interviewed Sam Bean from U.com, he described this idea of like a vertically integrated search engine. So say you want to search through just Reddit or just Wikipedia. That's one case where you then would put this filter on the vector search. And maybe if we could just talk through some more examples of filtered vector search and what that looks like.
Yeah, that's a great example. One that I always think of, because I think where users are most used to filters is e-commerce. Like if you order something from a web shop, you would, let's say you would filter the price range because you want your object to match a specific price range, or you would filter it by specific product attributes. So if you're looking for a new VV8 t-shirt, it has to be navy blue, and then you put navy blue on it, and then you'll get the right one. Not for me. I only wear black shirts, I guess. No, but these are the kind of applications where users are so used to applying filters, maybe without even being aware of it, because it's just natural. And then, yeah, as you said, I really like this idea of having a massive data set and sort of narrowing it down on the fly. You're saying, well, now I just want to filter by, only search through Reddit, for example. And by having that sort of big vector space and having the ability to set those filters on the fly, you also don't necessarily need to know upfront, right? Because you could also say, if, say, a vector search engine wouldn't support filtering, you could just say, okay, I'm going to split it up front. I'm just going to, here is my collection for Reddit. Here's my collection for, I don't know, the next thing. And then you search them one at a time. But that only works if you can predict entirely what these kind of combinations are. But if you can dynamically sort of combine these filters, and that is also something that VV8 already supports, but that will be way faster with bitmap indexing, just because it's so cheap, such a cheap operation to do like an intersection on on two bitmaps basically. So you can do that dynamically. So it gives you sort of more flexibility later on. Like, yes, there are cases where you maybe want to optimize something by splitting something up front. Like, I'm not saying that those don't exist, like in those hyper optimized cases for one use case, but in the general, just throw something at it, let VV8 deal with it, and figure out what you want to do later without being sort of blocked by a previous decision. That's nice, and that's going to be much faster now than it was before.
Yeah, that example of chaining together the where filters is so interesting. Like navy, like a t-shirt, navy blue, price between $20 and $40. I'm not sure how much this shirt costs, but like, we're using my shirt. But yeah, so another question I got when I was at the New York meetup, Weaviate meetup, was about role-based access control. Would this enable that?
Ooh, interesting question. Yeah, so yes and no. So there, if you want to do, or it depends a bit sort of where you do your role-based access control. So maybe for people who aren't aware, role-based access control is basically a very fine-grained access control mechanism where different users have different roles, and then one role grants you rights to specific things. So basically, by default, you have no rights to do anything, but then you could have specific roles, and basically through those roles, you inherit permissions to access something, whatever that something is. That could be something in the context of the application, could be something in the context of VV8, basically a specific object. So if you do set such a property on your VV8 objects, and then in your application, you would make sure that you that you set those filters to match either the specific roles or the specific permissions. You could definitely do that with those filters. The sort of downside, or maybe not downside, is just sort of it's a engineering decision, and it has trade-offs. And basically, What you need to do then is make sure that the user can never find a path where they can basically skip that kind of filter. Because like if for example there was a way that they could all of a sudden have an unfiltered search, and they would search across basically everyone's data, which is of course what you want to prevent. So depending on your kind of security requirements, it may also make sense to have the role-based access control directly in the database and not sort of on top of it. But that's basically that you need to decide that from a use case to use case perspective of how you would want to integrate this. This, by the way, also a question that also comes up every once in a while, and I've been meaning to write a blog post about it, but I haven't yet, is multi-tenancy, because I guess sort of the role-based access control is very similar to the multi-tenancy case, where you would have, say, your users are grouped by something, and then how do you represent those user groups or their companies or whatever it is that associates them to one thing? How do you group that in VV8? And typically, what we do there is we do it on a class basis, because that sort of gives you, and that's why I'm bringing this up, as opposed to doing it in a sort of monolithic large class and then set individual filters. If you have it per class, then you have that separation. Like the way that a class is created in VV8, it's like everything is isolated. Basically, it's a separate folder on disk, it's separate files on disk, and there's basically no way that one tenant could influence another tenant. But that said, multi-tenancy is also not the exact same thing as sort of fine-grained access control. So, but these topics overlap. So I thought that would be worth mentioning as well at that point.
Yeah, that's extremely interesting. So I think that's a great coverage of bitmap indexing, beginning with the technical details and then, talking about the applications, the filtered search. And I think it's important for people to know that you can filter the vector search. It's not just vector search. You can also add these symbolic properties, add things to your data like you would with any kind of data management system. And you can achieve faster vector search by filtering with the properties. And that's probably one of the most exciting things in my opinion. I love this kind of filtered vector search thing. So then stepping into the meat of the vector search, the vector index. So HNSW-PQ, what does product quantization add to the table?
Yeah, such a cool big topic, and I'm so happy that we finally have the first release. So I think we teased something late last year already when all of us were together in Italy, and this was one of our presentations that we had there, where the overarching goal is basically to reduce the operating cost, which is mainly driven by memory consumption. So sort of goes hand in hand. Like if you want to look at it from tech perspective, we want to reduce memory usage. If you want to look at it from the business perspective, we want to reduce operating costs, but really it's the same thing. That was driven by sort of, okay, how can we get the usage down basically without sort of making any sacrifice? I mean, what you could do is turn off the vector index. Like that would reduce your memory index, but it would also make it kind of pointless to use VV8. So yeah, how can we give the same kind of quality to the user while making it a bit cheaper to run? And there we have basically this two-step approach to it, and HNSW-PQ is the first step. The second step, starting with the sort of longer goal, is a fully disk-based solution. So disk-based solution basically means what's on disk doesn't have to be in memory, so therefore it's cheaper, and SSDs are fast. And if you optimize it for SSDs, there are certain ways where you can make benefits of those disks and still have a very similar experience. That said, there's also sort of like you can never run any kind of program without memory, right? Like if every little thing was loaded from disk the minute or the second or the millisecond or nanosecond that it was used, it would become very, very slow. So you can basically put parts to disk, and you keep some parts in memory and put some parts to disk. And the kind of idea in any disk-based system. So Abdel, for example, published this comparison of Vimana, which is what Microsoft's diskANN uses, which technically is quite similar to HNSW because it's also graph-based. It's a single-layer graph instead of a multi-layered graph, but it's still very, very similar. So basically, with all of these systems, you need to keep something in memory, and the idea is you keep sort of something small and cheap in memory, and have the large and expensive stuff put to disk. And now to loop back, sort of what is the small and cheap stuff that you can keep in memory? And what you find in all of these ideas is compressed vectors. And this is where product quantization comes in. So we had Matthijs Dues on the podcast, which is basically this deep dive into product quantization. So he explained this way better than I could, and than I could in like 30 seconds. But the general idea is that product quantization is a form of compression. It's lossful compression, so it's not lossless compression; it's lossful compression, and you can tune it. In the simplest case, you would have a single float 32 dimension, which originally in the continuous vector is 4 bytes, would be turned into a single byte. So you'd have a 4-to-1 compression, but then you can basically compress it further by having multiple dimensions per segment. So you could get to like 8-to-1, 16-to-1, 32-to-1. And this comes at the cost of dropping recall. So as with anything, there's some sort of a sweet spot, which is if you want to have the exact same kind of quality as you have with HNSW right now, then the sweet spot is probably 4-to-1 compression. But if you say, well, I care less about recall, I care about running billions of vectors cheaply, then maybe your personal sweet spot is at 8-to-1 or 16-to-1 or 32-to-1. And where Abdel is currently working on a blog post illustrating these kind of trade-offs. Anyway, long story short, compression is a vital part of any disk-based system. And we thought, well, we're currently developing this disk-based system and it has a certain timeline, but can we create value for the user sooner than that? And then we thought like, well, HNSW PQ is basically half of disk data. It's like the 50% of disk data, and it has the compression. It still has the vector index. And the only difference really is that the vector index is still in memory and not on disk. But the vectors, if they are compressed 4-to-1, then fictional example, let's say your current memory usage is 10 gigabytes. Of those 10 gigabytes, 2 is the vector index and 8 are the vector embeddings. Then, and now I'm glad I chose round numbers that are easy to calculate. Then if you compress those 8 gigabytes of vectors by 4-to-1, then they would turn into 2. So basically your you still have the 2 gigabytes for the vector index plus the 2 gigabytes for the compressed vectors. So instead of 10 gigabytes overall, you now have 4 gigabytes. So you basically had a 60% reduction in memory usage. And 4-to-1 is such a low compression that you're probably not even going to notice the drop in recall. So it's like almost free, almost for free. You've got a 60% reduction in cost. And then I said you can drive it even further.
Yeah, that's incredible. And Abdel has done such an incredible job with this blog post. I'm not sure if this is if the blog post is published when we're publishing this, but I highly recommend people checking this out. This blog post really helped me firstly understand the memory requirements of HNSW. The blog post describes the calculations of with HNSW, you have this max connections parameter, and then you have to store this number of parameter connections, and with like int16 and describing the details of what that creates in overhead as well as the compressed vector as your calculation with the 8 gigabytes, 2 gigabytes, and that reduction. And then I really liked what you said about like if your goal is just to run 1 billion vectors compared to 1 million with the recall trade-offs, basically you have this decision of how you want to group the vectors. So like if this is a 32 dimensional vector, you know segments of 2, right? And so that's how whether you increase that, you'll compress it more, but at the cost of lower recall. And it comes back to that, I think, ANN benchmarks thing you did with the, showing the recall of approximate nearest neighbors. Yeah, I think all of that is just so interesting. Something I'm really curious about is explaining further the k-means and how that's used to cluster the vectors and kind of what the overhead and the thinking is behind that.
Yeah, so for the compression algorithm, basically to reduce the amount of data, you need to sort of build groups. You just said that example of taking 2 dimensions and putting them into like groups of 2. So then the questions becomes, what identifies a group? Like, how do you pick your groups? Because you could pick them very, very bad, basically, where the distance between 2 points in a single group would be very large. And then if you put all of your groups sort of on top of each other in a graph, all your groups would suddenly be identical. And then you'd have the problem that well, what's the point of having this many groups if they're all the same? So basically you need to pick your groups without going too deep into how product quantization works under the hood, but basically you need to distribute your data in groups that have no overlap and where something that's within a group is actually similar. Because if you use that for approximation, then yeah, If it's dissimilar, then basically that's why your recall drops. And k-means is a very simple clustering algorithm to that basically does exactly that. So if you imagine all your vectors on like a 2D graph plotted somewhere, there are naturally going to be clusters, and then k-means is just an algorithm that identifies those clusters, and it's by no means perfect, but it has like an exit condition basically where it stops running if it can't improve further, and then you have ways to sort of run it over and over again to find like the best possible clusters. And that is essentially what's used in PQ. These kind of it's like I would say the initialization in PQ is this k-means, or these k-means clusters, because these clusters then represent the individual segments in product quantization. And then something that I think that will also be mentioned in Abdel's blog post, or has been mentioned depending on whether it's been published already. You don't necessarily need all your vectors to produce a good PQ codebook or good PQ clusters. So in the example that he runs in his blog post, I think he uses 20% of the data. And then it runs under the assumption that the remaining 80% of the data is distributed in a similar way as the initial 20%. And like this assumption becomes true depending on the size of the data set. And of course, if you think of your data set in real life topics, if your first 20% happen to be about navy blue VVA t-shirts, and then your remaining 80% are all of a sudden about car parts or something, then that distribution, that assumption doesn't hold true. But typically that's not the case. Like typically you have like a slice of your data that's somewhat distributed, and then if you add like a light blue t-shirt, then it makes sense that you would find the existing group for the light blue t-shirt. And then if you add a new headlight, then the LED headlight would be close to the whatever incandescent headlight that's already in the, I'm not sure if they're so used anymore. But it kind of runs under the assumption that these clusters still make sense, and typically they do, which is nice.
Yeah, that notion of like distribution shift and how it applies to vector index structures are super interesting. I read this paper OOD Disk ANN that touches on this problem, and I definitely think that'll be something that to keep an eye on. I find the k-means thing to be so interesting. Like for example, we were comparing k-means with UMAP on our BERT topic podcast, and in the case of BERT topic, you're trying to cluster vector spaces to understand the similarity between clusters. So k-means has a bias on trying to evenly distribute the space with the centroids, which makes a ton of sense for product quantization because you're trying to compress the vectors with the centroid IDs. So it works great for that. Whereas UMAP is better for like if you want to have some odd shape. Where Martin uses this example where it's like a circle with a dot in the middle, and k-means would just try to like cut that up rather than clustering the circle around the dot. So it's very interesting to think of the trade-offs between the clustering algorithms. It's very cool to see the k-means implementation in Golang and Weaviate, and seeing the clustering coming as a part of the vector analysis stuff as well. So awesome. So I think that's so exciting, the opportunities with reducing the memory requirements of vector indexes, and all of that, making it more accessible to create billion scale. Maybe if we like dream a bit about this, like how much can these kind of savings help people with scaling up their clusters or the things they imagine doing, but limited with the cost and thus needing optimizations like this?
I think the biggest sort of enabler, or this is going to be a big enabler for cases that don't necessarily have a lot of traffic but have large data sets. So if you think of the other data set, let's say someone's building a new type of search engine, and that would hit millions of requests per second, they would probably not mind that the setup is relatively expensive, because just to be able to serve millions of requests per second, you need large infrastructure anyway. So it doesn't matter that the memory requirement is a bit higher, because you have, tens or hundreds of CPUs anyway. So that kind of goes hand in hand. But for those cases that are maybe, and I think we also find them a lot in the sort of more analytical space and maybe on the research side, where you have a massive data set, but your requirement is not necessarily to get like real-time information. If the query takes a bit longer, or you do it async, that's fine. Your goal is basically to get that information. And then you can't justify having a cluster that costs like multiple thousands of dollars a month. Then you need a cheaper way. And in that case, you're also probably very happy to trade off performance because, well, you don't have that many concurrent queries. And that is, I think, these cases are going to be enabled because you can easily just say like, okay, here 50%, 60%, 70% cost reduction. And that's only the first step, right? Like with if we get the go for the full blown disk based solution, then the reduction will be even further. But already, I think we can enable these kind of cases where VV8 maybe right now would be sort of a nice solution, but just isn't viable, and then it becomes more viable for these.
Yeah, that's super exciting. Super cool. So if we're pivoting topics a bit, we have two more like kind of update things, then coming back into a speed improvement, another algorithm to talk about. Could you explain the Cursor API and what that adds to Weaviate?
Yeah. So we have, I think, in this release, and the other one we haven't talked about yet, but in this release, we had the two highest or most requested feature requests from our community. And the second one that we're going to talk about later is now the highest, the most upvoted one. But before that was the case, this one, the Cursor API, was the most upvoted one. And the Cursor API is, if you think about it, it's a super, super simple construct, but it's so useful. So before the Cursor API existed, if a user used VV8 as their primary database, then at some point they might have a requirement, could be for auditing purposes, could be for something completely different. But basically the requirement is, how do I, or the question that they would ask is, how do I get all of that data out of VV8 again? And then in the past, we would say, well, that's kind of like VV8 isn't designed to get your data out. VV8 is designed to get your data in and then search your data. And you can, like, if you find the right search queries, you can find everything that's in that database. But there was basically no way to get it out. And then people would try to use like the pagination feature as a workaround. But the pagination is built in a way where basically each higher page becomes more expensive than the last. So you could do that to a certain degree, but then typically after 10,000 elements, you would run into some sort of an error message where VV8 would tell you you've reached your, I think it's called query maximum results. And you could increase that, but there's also warning that comes with a higher cost and that you shouldn't necessarily do that. And now if you want to get 1 million or 10 million or 100 million objects out of, basically there just was no way. And then you could build a workaround where you would, every 10,000 object, you would assign a field to a unique value. So you could set like a page property on your object, like a fictional page, and then every 10,000 you increase the page, and then you could set a filter, give me page 7 or something, and then you could get those 10,000 that would match the fictional page 7. But that's, of course, super complex. So all of that, throw it out of the window, don't have to do it anymore. Now we have the Cursor API. And the Cursor API is a super, super simple construct. You basically start somewhere with an ID. And if you don't know where to start, then you just start with nothing, basically with an empty ID. And you say, give me 1,000 objects from the database. And then from that list of 1,000 objects, they are in a specific guaranteed order. And the last one, you can take the last ID, and then you can just take that ID for the next page, so to speak, to VV8 and say, give me the results after this ID. And then you get the next 10,000. And the cool thing is that this query has a constant cost. So it doesn't matter if you've already retrieved 500 million objects and now you want the I don't know how many page basically to get the next object. It always starts a new sort of retrieval process at that point that you specify. And now you can, in constant time, basically get every object out of your database, which makes it, we've added the backups feature, which allows you to get every object out if you want to get it back into VV8, basically. But now you can also, if you want to pipe it into a different system, like you could use that to stream your data to something. Let's say you would have a specific, or let's say you want to train a model based on data that's in VV8. Then how would you get all the data out of VV8? Well, you can do that now with the Cursor API. And you could either do it in one go and basically just export it and put it maybe in a Parquet file and use that. Or you could do it on the fly and sort of go through the cursor and do something with it.
Yeah, that case of training the model is what inspired me to click on the thumbs up on the roadmap thing. And yeah, it's very interesting, like getting the data out. I can imagine, like, just for the case of you maybe just want to have your data somewhere else again, just because it's your data and you want to have it as secure as possible and as active as many times in as many ways as you can think of, I guess. Yeah. But this kind of idea of getting the data out for the machine learning models, I think that's so interesting. I also think you could use Weaviate to retrieve the next batch of training data. kind of similar to Mosaic ML released this streaming data set thing. And I think Weaviate could be used in a similar way to get batches of data for training. So yeah, all of that I think is extremely interesting. So if we could also come in now, pivoting topics again. So adding the filters to hybrid search, maybe first we could start with just like what it is, and then I'm very curious what the technical challenges behind this were.
Yeah, so this is the other one that was most requested. So in 1.17 we released or we had BM25 support before already, but I think it was considered experimental, and we removed that flag, and then we said like here it's general availability in 1.17. But it did not support setting filters yet. So it's exactly the same kind of use case as we talked about before on filtered vector search. So same, we can use the same example of the navy blue T-shirt or combine it with price tags and everything. And you couldn't do that on a BM25 search. And in turn, because a hybrid search is both a BM25 and a vector search, that also meant you couldn't do it on a hybrid search. So in 1.17, we had this awesome new feature of hybrid search, which we see that it can improve the results running it over a specific data set benchmarks. To enable it, you see that you can get a higher NDCG score and higher recall and everything, which is super awesome. But now you're missing that kind of other functionality that Weaviate already has for vector search. So it was only a matter of time. And this was accelerated by, I think, our community upvoting that ticket like crazy. And it really became the most upvoted ticket very, very quickly. And yeah, that's in Weaviate right now. So you can now, nothing changes from a sort of, or if you, let me put it this way, if you've used a filter in Weaviate before, you already know how to use the new feature. Like it's literally the same where filter. And the only thing that's different now compared to 1.17 is that error message goes away that tells you filtered search is not supported yet. And now you can do it. From an implementation perspective, filtered BM25 search is actually not that difficult because we already have the inverted index, which we use for vector search, which by the way also means that these features that happen in parallel, like if you set a filter that's using the bitmap index that we talked about before, then all of a sudden these will also now be much faster. So there, the good thing is that these two parts are a bit decoupled. So that wasn't necessarily a big change to get them working into Weaviate. However, we've also completely rewritten the way that we do BM25 scoring, because in 1.17, the initial release was a sort of let's call it a primitive approach where we'd literally score every term that was matched. But now we've introduced the WAND algorithm, which is another way to improve the retrieval a bit. And then that tied in nicely with the filters because we just did that all in once.
Super cool. And yeah, awesome. So yeah, that's very interesting. How I was very curious, how the allow list kind of concept generalized to the BM25 scoring with the inverted index, and the connection to the bitmap indexing. That's also interesting. So maybe stepping now into the WAND algorithm. I had to give Dimitri Khan credit for, he's the first one who kind of taught me about this kind of idea where he's like, oh, you could probably have some way of sorting the terms. So when in BM25 you have a query like how to catch an Alaskan pollock, I like this query, and you you start scoring how to catch with the matching, and you can probably have some efficient way of scoring the documents. Like these have matched so many words so far that it's like highly unlikely that the match would be high enough. So I don't know if that's the exact algorithm behind WAND. Could you explain what the idea is with WAND scoring?
Yeah, that's exactly the idea. So you have in a BM25 index, or in a let's say in full text search, and this is something that traditional search engines have been or have provided for quite some time already. Now you can also get that in Weaviate. In full text search, you have specific keywords. So in very simple terms, TF-IDF or BM25 basically rewards terms that are rare. So in the how to catch Alaskan pollock, the how to is probably super common and doesn't really add any value to the search query. But Alaskan already sort of narrows it down quite a bit. So ideally in your search, and so maybe to step one step back, scoring everything that's in that term has a certain cost, right? So because we use the inverted index, that means the inverted index will tell us every single document that contains a specific term. So for Alaskan, that's very few documents compared to overall. Unless your entire database is about Alaska, then I guess that wouldn't be true anymore. But then you'd have another query in that term that would be, or if your entire database is about fishing, then yeah, same thing. So basically, there's always going to be frequent and rare terms, and ideally you want to give more weight, so to speak. But I'm not talking about weight in the sense of changing the calculation, because the calculation, like the score, is going to be the same, but more weight in the sense of I want to tackle this first because it adds more value, and then maybe I can skip something else. So that's why it's also called dynamic pruning algorithms, because you want to prune the stuff basically that you don't need. So if in a classical inverted list or inverted index a kind of scenario, the database doesn't know upfront which term is which, right? Like it doesn't have a sort of semantic understanding, and it does with hybrid search because of the whole vector search part, but the full text part doesn't. So now you have these like how, which matches so many documents, and then you have Alaska. I'm just going to narrow the query down for example's sake. It's just going to be how Alaska now, which doesn't make sense anymore, but it makes it easier to explain. Yeah, basically you have these many matches for how, and these few matches for Alaska, and you know how much each term can potentially contribute to it based on the BM25 scoring. So basically there's a maximum, and this is from this TF-IDF calculation, it's also part of BM25, there's a maximum contribution that each term can make. So now if let's say you've not had one, but you've already started scoring 20 documents maybe, and your top K, so basically the user-defined limit is, let's say it's 20. So you already have 20. That means you now have 20 scores already. So now you know basically that, let's say the BM25 score of the worst of those 20 objects that you have is 17, made up number. Now you know that if a new object cannot reach score 17, you can discard it. And how would you find out if a new object can reach 17 is basically you look at the maximum contribution of each term. So let's say the word how, and this gets nicer if you have a longer example, but for simplicity's sake, I'm going to stick with this how Alaskan. Let's say the term how has a maximum contribution of 3, and the term Alaskan has a maximum contribution of, 15. Then if those two are combined, that's 18. That's good. But if they're not combined, if you only have how, you can no longer reach your threshold. So basically what that tells you, and this is everything that the one algorithm does, it tells you skip every object for how that doesn't also match Alaskan. And this means then if you have these like sort of relatively dense list, which is the one with how, which is dense because there's so many matches, and then you have the sparse list for Alaskan, which is rare, at some point those lists are going to overlap. And basically it allows you to sort of move that pointer ahead to the next point where they overlap, where you have the minimum possible score to reach. And then same goes on basically. Let's say you manage to skip 5,000 matches for how, because only then you would find the next ID that matches both how and Alaskan. And then after that, there's another 5,000 which only match how. You can do the same thing again. And this way you can reduce the amount of scoring drastically. Like in the most extreme case, you could reduce it to the number of scores for the word Alaskan and almost sort of ignore the word how. But of course, if the difference is not that extreme, then you don't want to completely ignore it. You just want to sort of, not score it if you know that it's mathematically impossible to reach a higher score, and then you want to skip it. And that is what makes that algorithm super cool, because in the context of vector search, we deal with approximate algorithms a lot, but this is not an approximate one. This is really just a smarter way of scoring, basically, and the score in the end is going to be exactly the same.
Yeah, that is so interesting to hear about this sparse scoring algorithm, and maybe talk a little more about sparse vectors. But just quickly, like I've plugged in this WAND test into the Beer test with natural questions, and for me, evaluating natural questions is 2.6 million documents, and this time is how long it takes to evaluate the NDCG of 3,500 queries. And the difference before and after WAND is like 5.5 hours to like 14 minutes. And this lets you, so I was like, wow, this is pretty exciting. Just anytime you see that kind of thing. It's similar back to when you had the 1,000 speed up with filtered search.
Exactly.
Yeah, those things are always like the eureka thing to see. But yeah, I think it's so interesting. Like, I did a little research into one, and I saw the paper from 2003 that proposed this, and I think it's so interesting to see it still being used. And I also saw this other idea of splayed sparse vectors, where we use deep learning models to create sparse vectors. So the idea being you have how to catch an Alaskan pollock, and you put the language modeling head on each of the tokens, and then you get a distribution over the vocabulary that comes out of the language model. So I think pollock would probably be the best one, because maybe like in addition to pollock, the language model might have thought it was like salmon. That would make some sense, right? So it would so you'd have this sparse distribution, and it would be the same kind of scoring building blocks, as far as I understand, for how you would index that particular kind of sparse vector, and then retrieve it efficiently. But yeah, the whole thing, hearing about the thresholding algorithm, it's all so fascinating. So super cool. So yeah, I think coming out of some of the speed things, and now something that is into the database thing. So what's new about replication?
Yeah. So I think today, depending on who the audience is, either they have to wait a very long time to to get to the parts that they're interested in, or they're going to learn something completely new, because we have so many. Like, this is such a diverse kind of release. Like, we provide value in so many different areas. Like the bitmap indexing, I guess, was sort of also more on the databasey side, maybe easier to grasp, and the PQ is sort of completely in the nitty gritty vector indexing thing kind of side. But yeah, coming back to sort of the good old distributed system kind of replication topic. So we released replication in 1.17, and something that we made very clear in the beginning is basically this is the feature set of what replication can do, and this is if this is sort of good enough for you, then use it. This is what we're going to do in the next couple of releases. And if you have a certain point where you say, like, okay, I need this particular feature, then you can sort of start using it that specific point, and it's just going to get better and better over again. So sort of the idea is to release this in chunks or in increments, where it constantly gets better, and you don't have to sort of wait over and over again, because 1.17 probably covered 80% of cases, but then you have those remaining 20% basically that take much longer, but also that there may be a requirement for some cases, depending on what you want to do with replication. Replication to me is such an interesting one, because the motivation of why someone needs replication in their database can go anywhere from they have a specific failure scenario that they need to protect, and where they need to make sure that if A happens, the database doesn't go down, and that a database can still read or can still write, or these kind of things, all the way to they need to sign off some sort of a corporate sheet where there's some sort of a compliance policy that they cannot use a system that has a single point of failure, so everything needs to be replicated. And we're seeing all of those. We're seeing like people who need replication for the actual value of replication. We're seeing people who just need replication so they can tick some sort of box and say, like, okay, VV8 has replication. And yeah, depending on where you sit on that line, I think different points and different features add more value. That said, that was all the sort of the long introduction of how we release replication in smaller chunks. But what's new in replication in this release is we now have tunable consistency for every single endpoint, or I think almost all endpoints. And this is so tunable consistency is modeled after Cassandra, which in our opinion, like basically we looked at, okay, what's out there in the space and what behaves in the kind of way that we want VV8 to behave. And then Cassandra with its hyperscale kind of capabilities was a very good role model for this basically. So tunable consistency is something that's modeled after Cassandra, where basically you as the user can make that kind of trade-off. How consistent does this read or write have to be? And the most extreme case would be all, where you say like you have your database replicated 3 times, and then you make a write with consistency level all. That means that request is only going to be successful if every single one of those 3 nodes acknowledge your write. And if one doesn't, then the request fails. But then you could also have the other extreme, which would be consistency level 1, where the idea is that only a single node has to acknowledge the write. That doesn't mean that only that node owns the data. Like the data is still going to be replicated to the other nodes. But let's say node 2 failed and now it can only be replicated to node, well, let's say you're hitting node 1, and it can be replicated to node 3, and node 2 is currently down. This would still be allowed with a consistency level of 1. So basically, in this case, your request would still succeed. And that can be desirable because this gives you a kind of scenario where you can still write even if a node is down. And why would a node be down? Well, could be because it actually like hardware failure or something is broken, but it could also be something that's planned where it's down for a very short time, for example, because you're doing a rolling update. So you could say like, I want to upgrade VV8 from 1.17 to 1.18. Then each node would be in this rolling restart kind of fashion, would be down for a very short time. And if in that short time period something happens, now you have a full control. Do you want strong consistency? Then you probably write with consistency all, which means this request will fail and you have to retry once it's back up again. Or you could do it with 1, where basically it will be replicated later. Or you could do it with a quorum, where the idea behind a quorum is basically that it's a fancy term for majority, basically. So a majority of the nodes has to be present. And then if you use the majority both during writing and reading, then you always have the guarantee that it has to match. Because if a majority of the nodes have received an update and have confirmed receiving an update, then when you read with the majority, there's mathematically no way to get the old stale data. So these are the kind of trade-offs that you can do and really configure this for your needs. And then there's the second new part, which is read repairs, which to me is like the first time I used it, I was blown away by how simple it is and how effective it is. So if we're sticking with this kind of situation where a specific node was down during an update, and you accepted it because you said, okay, my consistency level is, say, just quorum or maybe even 1, then how do you deal with it when the node gets back? Like, because at some point that node is going to be out of date, right? And if then you read with just consistency level 1, and there's very good motivation to read with just 1, because that means your throughput can go up. Like if basically every data is always replicated and you read with just 1, then now you have not one node that can serve all the data, but now you have 3 nodes, and you could also add a 4th and a 5th and so on. So there's very good motivation to read with consistency level 1. But now what happens if that node is out of date? Like, if you happen to hit the node that didn't receive the update, you would be serving stale data. And you can prevent this by setting a higher consistency level, of course. But also this is where the eventual consistency of VV8 basically, and that whole design comes in. If you don't want to read immediately with a high consistency level because it has a higher cost and lower throughput, you can rely on the fact that eventually this will be consistent. And one way to repair the data, and this is new in 1.18, is the read repair. And the read repair basically says if you query the object with a, let's say, with a quorum consistency level, and VV8 realizes that, let's say, 3 nodes and 2 are queried, and one of them is out of date, VV8 will just repair it. And VV8 knows exactly, based on timestamps and based on other kind of metrics of what happened, VV8 knows who of those 2 nodes is wrong, who missed the update. And then if you query it with that read repair, by the time that your query is returned, the data is already repaired. So you won't even notice, like you can query exactly the node that had the stale data, but as part of the query, and that's why it's called a read repair, basically as part of reading the data, VV8 already repaired it in the background. You'll receive the right request. And that was the moment when I tried this out for the first time. Like I tried to specifically get my database in an inconsistent state by actively killing a node, then making an update, making sure that the node missed it, restarted it, try to query it and forgot to set the 1 consistency, and then defaulted, I think, to either quorum or all. And immediately it was already repaired by the moment that I got the response. And I was like, wow, this is exactly how it should be. Like, this is so cool because, if you really want to fine tune, you got all the ways, but also if you just want your data not to be out of sync, then let just be it, just let it repair itself.
Yeah, it's amazing. And I really liked how when we first started talking about replication, you had like the Black Friday e-commerce example, and understanding these kind of trade-offs with read write and when you need certain levels of consistency. Yeah, that read repair thing is so interesting. I think this would be also a great transition of, you've recently given this amazing lecture on our journey to build a vector database in Go, and this is published on YouTube if people are interested in checking this out. So a question I have with replication, these kind of things is, maybe you could touch on what features of the Golang programming language help build things like this, like distributed database systems.
Yeah, that's nice because my talk was basically about what features of Go are hindering us from building the best possible database. No, that's not true because it also has a solution for all of those challenges. Um, Features in Go that really work well is, I think, the main two things that come to my mind right now is, one is dealing with concurrency, because especially if you have these kind of background operations, you may have to spawn, like in Go, you don't spawn a new thread, but you spawn a Go routine. A Go routine is basically like a lightweight thread, but then you can have, because it's so lightweight, you can have way more than actual physical hardware threads, and then the Go runtime will just manage it for you. And it gives you lots of tools to basically make sure, because the moment that you have concurrent processes, there's always a risk of data races, and the whole tool set in Go, both during development as well as for how the language is structured, really makes it easy to write thread safe or sort of safely concurrent code. So that's one of the parts that really help well there. The second is the strong standard library. So this is something that, depending on so I, way back before I started writing Go, I used Node.js because that was sort of the thing at the time, and I also did some front end work, and then at some point moved into back end work, and then it was with Node.js. And in Node.js you have the exact opposite. Sorry. So basically, anything that you do, you have to import a package. There was this, I think it was called the left pad fiasco at some point, where a package that would pad a string on the left side, which is like one line in any language, even in JavaScript, that's just one line. That was an external package, and then this particular package had a security vulnerability, and I think it wasn't a security vulnerability. In this case, I think it was just deleted. I think it was just the author decided to delete this package. But the problem was that thousands upon thousands of packages or node programs and packages that were used everywhere in production depended on that one package, and all of a sudden all the builds started failing. So coming from Node, like way back in the day, like I was an early adopter of Go, so I don't even remember when that was, but it was really like way back. Coming from Node to Go, seeing how strong the standard library in Go is, and not needing these kind of third-party dependencies and these kind of third-party packages, that was such a both an eye-opener that you can do it just with the standard library, but also such an enabler, because there's all of a sudden you don't have to learn framework after framework after framework anymore. You just know that the standard library of Go, and it is somewhat sort of limited, but over time you feel like you know all of it. That's probably not true. It's probably way bigger than what people typically use, but it gives you a nice, sort of the commonly used things. You just know how to use them and don't have to look stuff up, and just by just typing it or relying maybe on your code editor or IDE to do some auto completing, you can build basically an entire database. And that's not even a fictional example, because that's basically what we do in VB8. And to loop back in the beginning when we talked about bitmaps, we said that we took that crazy decision to build everything from scratch and not have many external dependencies. And that works super, super well with Go, because I think that's also the philosophy in Go, that the language is so powerful on its own that you don't need these third-party tools, but just what the language provides is there. And very practical example in replication, because we're dealing with the distributed systems where nodes have to talk to each other. There's so much network traffic going on, and there's multiple ways of how to do that. But basically, being able to do all of that just with tools that the standard library provides is super powerful and really keeps the iteration time down. So those would be my two favorite points about Go for a feature such as replication.
Yeah, that's so interesting. It's so interesting, like going into the Golang, and I mean the whole end to end. As we start off by talking about the bitmap, the HNSW, like vector search, deep learning, and then coming into the features of Golang, it's amazing. And maybe one other detail on your talk that I was curious about is, so yeah, as you mentioned, your talk was about the hindrances of Golang, and one thing was the stack versus the heap memory escaping to the heap, and I know we talked about the garbage collector. Maybe talk a little more about like the state of, I know the Go mem limit and all these kind of things, and like how that's been, because I understand that it's getting better. And
Yeah. Let me try to answer that from the perspective of a VV8 user, basically, because I think the VV8 user has two interests. Well, or basically in VV8, but in turn then also in Go. One is the application shouldn't just randomly run out of memory. Like that's basically the worst case. You sized everything correctly, you planned for everything, and then all of a sudden VV8 just goes bam, out of memory, kill. And the other is you want high performance, and these things are closely related because performance in Go often is a topic of memory management, which may not be super obvious because if you think of performance, you think like the bottleneck is your CPU, right? Like if your CPU does this many things per cycle, then it's fast, and if you can reduce the amount of things that it has to do per cycle, or I don't know, use a smarter way of doing it. Like in the talk, I talked about SIMD, for example, where you could do 8 operations for the cost of a single operation. That is what you immediately think about. But in a garbage collecting language like Go, often it's not CPU, or it is technically still CPU bound, but because of something that you do with memory, and that is where memory allocations come in. And the idea between, or the split between the stack and the heap, the stack is basically represents your function stack. So as you move through functions, you move through that stack, and you have variables with a very, very short life cycle. They are, as you start calling the function, basically the variables are created, or are avoiding the word allocated right now, but they're assigned basically. And then when the function is over, those variables can just go away. So they have a very fixed lifetime. Whereas the heap is everything, and that's why Go uses the term escaping, which I kind of like, because it escapes that clear function stack. And now, and this could be, for example, because it's shared between different function calls, or because the life cycle is meant to be longer than these individual function calls. So basically something escapes. And this escaping makes it way more costly. So both the process of escaping, because now the Go runtime has to say, like, okay, this needs to be tracked basically, and we need to find some space somewhere on the heap. But also then it needs to be deallocated again, because it's like now that it's escaped the function stack, it's no longer in this kind of predictable life cycle of when can we free it. And if you couldn't, or if you would ever lose that kind of association of how it could be free, then you'd essentially have a memory leak. You'd have memory that's assigned somewhere that you don't need anymore, that's still around. And then your memory starts ballooning and you don't know why. And that's sort of something you definitely want to avoid. And to avoid this, basically Go uses a garbage collector. It's a very good garbage collector, but nevertheless, something that's allocated on the heap is always slower than something that's allocated on the stack. So this is the kind of performance background in this kind of setting. But then I also said you don't want your application to just randomly run out of memory. And this was the biggest change in Go 1.19. I'm almost getting confused with the versions of, like, VV8 is at 1.18 right now. Go is actually at 1.20 right now. At some point, we have to start releasing VV8 faster than Go, so we can higher her numbers, which I think that the VV8 release cycles are way faster. So that's only a matter of time. But yeah, in Go 1.19, the Go runtime introduced this Go mem limit thing that we have a blog post about also. And Go mem limit does something that's actually it's one of those things that are super simple in hindsight, or once you know it, it's super simple. Go mem limit just says this is the limit of memory that you have available, and the garbage collector will try to respect that limit. And now the question is, like, why didn't it before that? Like, why wouldn't the garbage collector do that before? And before, the garbage collector had a tuning parameter that was relative to the current heap. So basically, and the default was 100%, which would mean that if you have a machine with 64 gigabyte of memories and you currently have 33 gigabytes of memory allocated, the next 100% increase would be to 66 gigabytes, bam, out of memory. So now you're at like 51% usage. And just because of the way that the garbage collector would try to allocate or try to, the collector doesn't allocate memory, but it would just delay running again. So basically it now would say, like, okay, I'm going to run again once the memory is at 66 gigabytes, but your machine only has 64. So that doesn't work. And all that Go mem limit does is basically give the garbage collector that kind of hint of where the limit is, and Go call this a soft limit, because it's just a hint to tune the garbage collector to run faster. And now the garbage collector basically knows, okay, I'm at 33 gigabyte. My limit is 64. So I'm not going to wait till 66, but maybe I'm going to run at 60 already. And all of a sudden, like you made use of that memory, that memory is there to serve whatever purpose you want, whether it's a purposeful heap allocation. So for example, in BB8, the vectors, or with HMWPQ, also the compressed vectors, they stay on the heap because that's what we want, right? We want them to stay around. But something that we do, for example, a filter that's used as part of a single call stack, that doesn't stick around, so we don't want that on the heap. But either way, no matter whether it's intended heap or unintended heap, now with Go memlimit, VV8 can or any Go app basically can respect that and make sure that it doesn't, quote unquote, accidentally run out of memory again, because that's really what it was. Like it just set the wrong target basically, and that's prevented with that. And I think at some point we also added a feature into VV8 specifically that marks your objects as read only if you get close to that threshold. So I think it's getting more and more, like, as VV8 improves and as Go improves, it's getting more and more difficult to actively manage to run out of memory, which is awesome for a user, because that essentially means it's more stable and harder to kill. And if you still manage to kill it, then you have replication, and then all is good, because that one node death doesn't matter because it's replicated. So
yeah, it's so amazing. It's so amazing, like the depths of the languages that build databases, the features of databases, and then the whole search technology more broadly. And so awesome. Eddie, and thank you so much for another Weaviate release podcast. It's very inspiring for me working on Weaviate to hear the depths of your knowledge with all these things. And I'm sure it inspires people who are using Weaviate already or are interested in checking out Weaviate. And I think Weaviate 1.18 is packed with so many awesome features with this bitmap indexing. To have these filters just as these like 1,000 times faster is obviously like just so incredible. The wand, the way that speeds up BM25 and sparse search, I've seen that myself. It's incredible. And HNSWPQ, all these things, replication, and yeah, just so exciting. So Eddie, and thank you so much.
Thank you for having me, and also big thank you, of course, to the entire team that actually built this. I am just here basically summarizing everything that we've done as a team in this sprint. But of course, we have these individual experts on all of these topics, and then that allows us, as you just said, to have a release with so many different topics that provide value. And I think this is really cool, and I'm super happy with our team and super proud of our team. So thank you, everyone, both inside Weaviate, but also, of course, outside our community for all the input and for telling us what the kind of features you need, what kind of features you benefit the most from, and yeah, any kind of feedback. Like, use Weaviate and tell us whether you like it. Also tell us if you don't like it so we can improve it. But please also tell us if you do like it, because that's awesome to hear. So motivating both for me and I think everyone on the team to hear the success stories with VV8 and these kind of. There was a tweet the other day where sort of father and son pairing did some experiment with VV8, and just reading that and reading the actual stories. This is so cool to change people's lives one at a time with VV8.
Yeah, that was an awesome tweet. The moment of like the father-son hacking with Weaviate. Amazing. Awesome. Thanks everyone for watching.
Thank you.
Bye.